Today we start the unit of electrochemistry. In it we will talk at length about oxidation-reduction reactions. Let's look at this reaction. It is our old friend, burning of magnesium and oxygen. During the course of this reaction, atoms of magnesium react with atoms of oxygen to produce an ionic compound of magnesium oxide. Let's look into details of this reaction, into how two types of electronically neutral atoms become charged particles. Each atom of magnesium initially has a charge of 0, because the number of positively charged protons in the nucleus are balanced by the equal number of negatively charged electrons outside of the nucleus. Out of the 12 electrons of magnesium atom, 2 electrons are valence electrons sitting at the most outer electron shell. Magnesium, being a metal, is readily lose those valence electrons. Each atom of magnesium involved in this reaction will lose 2 electrons. So we started with 2 electronically neutral atoms of magnesium. We end up with 2 ions of magnesium, each with a charge of positive 2. And overall, 4 electrons are released. In the meantime, a diatomic molecule of oxygen made of 2 electronically neutral atoms is aching to fill up the valence shell of the oxygen atoms with electrons to a full octet. Each oxygen atom is 2 electrons short from the octet. The molecule of oxygen will split into 2 atoms and each of them will accept 2 electrons, the very same electrons that were so nicely provided by the magnesium. 2 atoms of oxygen turn themselves into 2 ions of oxygen, each with a charge of negative 2. All 4 electrons lost by magnesium are now tucked away in the ions of oxygen. Magnesium lost 4 electrons, oxygen picked up 4 electrons. Positively charged ions of magnesium and negatively charged ions of oxygen got together to form a new compound, magnesium oxide. Oxygen went through the process of reduction. Its charge was reduced from 0 to negative 2, the consequence of accepting electrons. Magnesium went through the process of oxidation. It lost electrons and its charge went up from 0 to positive 2. Reduction is the gain of electrons by an atom or ion. It always leads to decrease in the oxidation number because negatively charged particles, electrons, are gained. Oxidation is the loss of electrons by an atom or ion. It leads to increase in the oxidation number since negatively charged electrons are lost. Redox reactions are the reactions in which both reduction and oxidation occur. In fact, one cannot go without the other. Our magnesium would not be able to lose its electrons if oxygen wasn't there accepting them. The oxygen would never get reduced if magnesium wasn't there shedding off its valence electrons. Please pause the video and answer the question on the slide. Oxidation and reduction occur simultaneously. Neither would be able to proceed without the other. To keep track of the number of electrons lost and gained in redox reactions, we use oxidation numbers or oxidation states. So let's look at the rules of assigning oxidation numbers. Rule number 1. Uncombined elements have oxidation number of 0. It doesn't matter what element we're talking about, whether it is diatomic or monatomic element, it is an element. It is a bunch of electronically neutral atoms. An oxidation state of them is 0. Rule number 2. In chemical compounds, the oxidation number is equal to ionic charge. This is great news for us because we know a great deal about ionic charge, and ionic charge over a considerable amount of elements can be predicted from their position on the periodic table. For example, we know that elements for group number 1 always become ions with the charge of positive 1. Elements from group number 2 always become ions with a charge of positive 2. Majority of elements from the group 13 become ions with a charge of positive 3. We can also rely on fluorine to become an ion with the charge of -1 and oxygen to become an ion with the charge of -2. These elements are very predictable in their ionic charge and consequently with their oxidation state. Rule number 3. Oxidation states of electronically neutral compounds must adapt to is 0. Dig out your reference table, open the periodic table and have it next to you. Let's assign oxidation states of the compound sodium chloride. Sodium is the element from the group number 1, so its oxidation state, oxidation number, is predictable +1. If you check oxidation states of chlorine, they are listed next to the element symbol on the periodic table, you will see that they are -1, +1, +5, +7, but considering that oxidation states of the compound must adapt to a 0, chlorine in this compound has an oxidation state of -1. +1 on sodium and -1 on chlorine together adapt to a 0. Now, here is dihydrogen monosulfide. Out of the two elements in it, I trust hydrogen to be a predictable +1. There are two hydrogens in this compound, each with oxidation state of +1, which taken twice creates a +2. It means that sulfur needs to be -2 to cancel it out. Here's another example, sulfur dioxide. Out of the two elements in it, I can trust oxygen to have a predictable oxidation state of -2. There are two oxygens in this compound, each with oxidation state of -2, which taken twice creates a -4. It means that the sulfur in this compound must have oxidation state of +4 to cancel it out. Sulfur trioxide, same story, oxygen is predictable -2. There are three oxygens in this compound, each with oxidation state of -2, which taken 3 times creates a -6. It means that the sulfur in this compound must have the oxidation state of +6 to cancel it out. Now, pause this video and assign oxidation states for the remaining compounds. Check your answers. Rule number 4. The sum of oxidation numbers in polyatomic ion must be equal to the charge of the ion. Okay, find the table of polyatomic ions in your reference tables. You can see that each ion has its overall charge listed next to it. Right now, find a hydroxide ion. You can see that it has a charge of -1. This is the charge of the entire structure of the ion. Let's see where it comes from. After all, both oxygen and hydrogen are very predictable in their ionic charge and consequently in their oxidation states. Oxygen has oxidation state of -2 and hydrogen oxidation state of +1. They nicely adapt to a charge of hydroxide ion of -1. Now, please find the sulfate ion. Overall charge of the sulfate ion is a -2. Here, we once again will trust oxygen to be -2, which taken 4 times creates a -8. It means that the sulfur in this ion must have an oxidation state of +6 to bring it down to the overall charge of the sulfate ion of -2. Now, let's look at polyatomic ion of permanganate. It has a charge of -1. Oxidation state of oxygen is a predictable -2. In oxygen we trust, which taken 4 times creates a -8. It means that the manganese must have an oxidation state of +7 to bring it down to overall charge of the permanganate ion. Phosphate ion has the overall charge of -3. Oxidation state of oxygen is predictable -2, which taken 4 times creates a -8. It means that the phosphorus must have an oxidation state of +5 here to bring it down to overall charge of the entire phosphate ion, which is -3. The polyatomic ion of chlorite has a charge of -1. Let's see how it works here. Oxidation state of oxygen, -2, which taken twice creates -4. It means that the chlorine must have an oxidation state of +3 to bring it down to overall charge of -1. Perchlorate ion looks a lot like our chloride ion, but let's once again assign oxidation states. The oxidation state of oxygen is -2, of course, which taken 4 times creates a -8. It means that the chlorine here in this polyatomic ion has to have an oxidation state of +7 to bring down the charge to a -1, the overall charge of this particular ion. Pause this video and assign oxidation states to all atoms and ions in these electronically neutral compounds. I'll help you with a couple of them. These compounds are electronically neutral, so the oxidation states of each compound should adapt to a 0. Check your answers. We said that hydrogen usually has an oxidation state of +1 or 0 as an element, and oxygen normally has oxidation state of -2 or 0 as an element. It is almost always true. Stick with this knowledge and it will serve you well. However, there are a few exceptions. They do not very often come up on the exams, but just in case. Peroxide. This compound here is electronically neutral. Hydrogen behaves as always, exhibiting its normal oxidation state of +1. But oxygen here in this compound is obliged to have an unusual oxidation state of -1, which is not normal for oxygen. Here, in this compound over here, due to its connection to ultra-electronegative fluorine, oxygen is even forced into an oxidation state of +2. But this is an exceptionally rare and unusual situation. Oxidation states of -1 and +2 are not even listed for oxygen in your periodic table. So please, continue to trust oxygen to have an oxidation state of -2 in pretty much any other compound. Those of you who indeed were following this video with the periodic table by your side, kudos to you. Probably noticed that hydrogen has 2 oxidation states, +1 and -1. +1 oxidation state is a norm for hydrogen in a compound. But occasionally, when hydrogen meets a metal that is super ready to shade off its valence electrons, instead of losing an electron, hydrogen is forced to accept an electron to its valence shell. As a result, hydrogen is forced to have an unusual oxidation state of -1. You can notice in these examples that in such cases hydrogen stands at the end of the compound formula as a negatively charged ion because it became one. Okay, that is all for today. It is a long video and rather full of details and important information. Maybe it's a good idea to return to it later.